Hello everyone, welcome to the very first video on cryptology. And when we talk about cryptology, the base behind it is math. And in math, the most basic concept, which is literally used everywhere in cryptology, is modular arithmetic. And most of you already know a bit about it, but let's start with absolute basics. So, what is modular arithmetic? It's all about remainders. So when you divide one number by another, whatever is left over is the remainder. So a mod b gives the remainder when you divide a by b. Let's look at an example. 5 mod 3 is congruent to 2 mod 3 is congruent to 65 mod 3 is congruent to minus 1 mod 3. Look at all these four expressions. All of them have got a remainder of 2 when you divide them by 3. And the triple equal to sign that's kind of equating all of them is known as congruence or congruent. Yeah, and we say it as is congruent to. And the remainder in all of them is 2. Let's proceed to some properties. So if A is congruent to B mod M, then we can say that A plus K is congruent to B plus K mod M, A times K is congruent to B times K mod M, and A to the power of K is congruent to B to the power of K mod M. In the third property, A to the power of K is congruent to B to the power of K mod M is used extensively in RSA for both the encryption and the decryption parts. So we'll see that in the future. We next move on to Fermat's little theorem, which states that if P is prime and does not divide A, then A to the power of P minus 1 is congruent to 1 mod P. Now we're not going to go into the proof, but this will be very useful in the future. Next theorem is Euler's theorem. If A and M are co-prime, then A to the power of torsion function of M is congruent to 1 mod M. And torsion function is denoted by phi of M. So A to the power of phi of M is congruent to 1 mod M, where phi is Euler's torsion function. Next, we'd like to discuss a specific aspect of this congruence. A times K is congruent to B mod M. Here, A, B, and M are given integers, and we need to find the values of X which satisfy this congruence. So certain conditions where you find a solution for X. So this congruence has a solution if and only if the GCD of A and M is equal to the GCD of B and M. Let me recall that GCD is the greatest common divisor. So only when both of them have the same GCDs will any value of X exist. The example here, 2x is congruent to 1 mod 4. We see that GCD of 2 and 4 is 2, while the GCD of 1 and 4 is 1. So because the GCDs don't equate, we can't find any solutions for X.
Now, if we see that the GCD condition is satisfied and it's equal to D, so that GCD of A comma M is equal to GCD of B comma M is equal to D, then we can say that this relation has exactly D solutions modulo M. A quick digression here. What do you mean by solutions modulo M? So I'm just going to give you an introduction to something called a ring for M. A ring of M is all the numbers that can possibly be remainders of M. So if I take some A mod M, what are the possible outputs that I can get? What are the possible remainders? So the remainder can either be 0 or 1 or 2 and going on to M minus 1. So all the numbers from 0 to M minus 1 form a ring of M. It's called a ring because if you take all the integers and then take mod M, it'll keep looping around this set of numbers again and again. It's a very basic understanding, but it'll suffice our needs right now. So what this is saying is, if the GCD is equal to D, then you'll have D many solutions in the range of 0 to M minus 1, both included.
Let's look at an example. 6x congruent to 4 mod 10 has two solutions. Why? Because GCD of 6 and 10 is 2, and that's same as GCD of 4 and 10. And the two solutions that satisfy this are 4 and 9. And notice that 4 and 9 are two values going from 0 till 9, that is inside the ring of 10. So that's it for this video. Let's meet again in the next video on Chinese remainder theorem. Bye.